Is annotation option disabled?
I think so. Yeah, I think I'll just ask Satya, can you enable that annotation option? One second, Dil.
Yeah, sure. Meanwhile, I will just go through the content. So what I prefer to cover in this session is we'll just go through the types of transformer implementations we can have, just a basic overview. Again, a detailed implementation lecture will take too much time, and it will be in too much depth also. So we'll just see what all ways we can implement a transformer.
Dil, sorry for interrupting. Yeah. I think the annotation option is not getting activated. Okay, is it fine? Or
okay, yeah, it's fine. Okay, I thought I will write in between. So yeah, I think I will go.
Okay, we'll just check it out.
Yeah, if it is possible, just activate in between.
Sure. Thank you. Sorry.
So I think you might have gone through the input embeddings and positional encoding in the theory part, but I thought I will just cover it over because that is very basic to any NLP application. So we'll just go through what is an input embedding and positional encoding, just a basic overview. And I would like to then introduce this NN transformer function in PyTorch. So an implementation based on NN transformer, again, a basic overview of that. And again, then I would like to introduce to Hugging Face transformer library. It is actually a very efficient open source API, and it has a lot of pre-trained transformer models where you can directly use for inference. And again, it has a lot of capabilities like you can pre-train, you can use a pre-trained model and fine tune it on your database. So we will just go through that also. Okay. Okay, so you might be now very familiar with this image, right? This is the transformer image. And this is very powerful architecture. Like since it has been introduced in 2017, there has been a lot of models developed using this transformer architecture. And in like how to implement this transformer, like you can actually implement it from very scratch. Like you can start implementing from this each encoder layer to can you see them? Okay, so from this encoder you can actually develop each of these modules and you can build a transformer. Like so if you want to build it from scratch, then you will have to define again multi-head attention as an option in PyTorch. You can directly call the function and you can start building from each of these layers. But it will be really a hectic task, a tedious process to build it from real scratch. And if you are using a complete transformer model, that won't do any better purpose. So again, in PyTorch, you have an encoder class and encoder layer where you can directly call this this complete box. I will just show a code snippet of how it is done, and you can do. But these options is better to be used when you have to change any underlying design aspects in this transformer. If you have to use this transformer box as such, then it is always better to use an NN transformer direct function. So I'm discussing this based on the PyTorch. In Keras, there are similar functions, but I will be covering based on PyTorch. Okay, so you can call the direct torch.nn.transformer function. So what you should know is when you call this class, what it is calling is from this, like the inputs to this transformer won't be this input. It will be after positional encoding. So this is the box which you will be calling for when you call this transformer NN.transformer. So that is a direct callable option library available in PyTorch, method available in PyTorch. So just before getting into that, I would like to just briefly go through over what do we mean by input embeddings and positional encoding. Can anyone just put on chat whether it is covered detailed in the previous session, the word embeddings or positional encoding? Can anyone just ping it over the chat? Okay, I think. Okay, then I think I'll again brief over what do we mean by input embeddings. Okay, so before you involve in any project of an NLP, what you should develop is a vocabulary. So what do we mean by vocabulary? You will have a text corpus, right? A training data set. It can be either the complete Wikipedia text corpus, or you can, another popular one is IMDb, or you can use any movie corpus dialogues which is available. So first you should develop a vocabulary. Vocabulary is a set of unique words. So like if you have to develop your own vocabulary from a data set, what you have to do is you should divide all the paragraph into different sentences. Then again, you will have to split all sentences into words. And then you will have to store each unique word into a dictionary. So that forms your vocabulary. So like a vocabulary can be, so also if you can have functions to directly build vocabulary. So like a vocabulary can look something like this. Okay. So these are the complete words in the vocabulary. Say that we have an input sentence like this: transformer is not flower, it is fire. So you cannot feed this sentence directly into transformer because the computer doesn't understand these words, right? So you have to convert it into numbers. So what you can do from a vocabulary is this dictionary, you can have the indices. So each word will correspond to a number, right? So now your input will be numbers. But again, these numbers directly doesn't make any sense. So what we should have is, because transformer is 7124 and is 612, these are just random numbers based on the indices. It doesn't have a feature encoding to it. So what we does actually is we embed each of these numbers into features. So like example, so like I want here for each word I am using 1, 2, 3, 4, 5, 6. 6 features to one word will be represented by this 6 features, and there will be values for each feature. Can anyone put in chat like what is the default feature dimension in the original transformer paper, or what is the feature dimension used in the transformers? Hi, can anyone just mention in the chat like, yeah, 512, correct. So it is 5. So you know that it's much bigger number than what I have represented. Right? So what do we mean by 512? A single word is represented in 512 dimensions. So then you can have a similarity, a cosine similarity, or whatever you have to have in this. Yeah, correct. Thank you. So 512 is the number of dimensions in original transformer paper. So again, in a normal NLP operation, it's always better to have more than 100 dimensions. Then only you can have a complete contextual representation of a word. So that is what we mean by embedding. And each feature you can think as a linguistic feature of a word. Okay, so like again in PyTorch you can directly call NN embedding by giving the length of vocabulary and feature dimension to directly build a embedding. And initially it will be randomly given, the numbers will be randomly given, and by after training these embeddings will be learned. Okay. Okay, so this is what is gist of what input embedding is. It itself is a big topic. Those who wish to do a lot of research or projects in NLP should really look on to this topic. There are a lot of word embedding options. There are a lot of models for word embeddings. So it itself is a big topic. I just wanted to give a basic idea what we mean by this embedding. Okay. In case of transformers, as you know, it is, even though it is handling sequence architecture, transformers are not working on a sequence to sequence basis. It is taking parallel inputs, right? That is one major advantage in transformers, because in other LSTM, GRU, or other attention RNN architecture, the inherent recurrence nature was there. So parallelization was not possible. But one major advantage with the transformer is that it was able to do parallel operation, at least in encoder. In the decoder, yeah, there was a sequence sequence dependency was there. But in encoder, we were taking, in multi-head attention, we are taking all the inputs parallelly. So, but the problem with that is the words are now not having any order. So we need to give position to each word. Okay. So for an example, these are 2 sentences, right? All the words in these sentences are same. Say I have to do a sentiment analysis. The first sentence, it's a negative sentiment. Second sentence, I will prefer it as a positive sentiment. Like, correct? Yeah, Arun sir. Okay, thank you. I'm sorry. Let me check once. I'm checking. I'm sorry, I couldn't find it yet. Yeah, I'm checking from the one which I'm sharing only.
Dil, we just enabled it, but I am not sure. Maybe sometimes if we may have to connect again, that may be the reason. I don't know. Just
Okay.
we just enabled it. Yeah.
Okay, fine. I think I will go with this.
Okay. Thank you. Sorry for the inconvenience.
It's fine. It's fine.
Yeah.
Okay. So like if you see these two sentences, you can see that the words are very similar, right? Or it's all similar. But the first sentence, that sentiment is negative, like sentiment, whatever application you are using. So you know that the position of the word does matter, right? So what can we do? But positional encoding, what we mean is that we have to encode a position to each. We can have to encode a value to each position. So we can say that she. This is embedding for the first word. Say it is she. So we'll add 0 because it's in the 0th position. Second word did is in the first position. So we can add positions like this to all words. But the problem with this approach is if the sentence is too long, the final words will be having a very high value for the position. We'll say like it's a 31 word long sentence, and the final will be 30 plus the embedding values. So that scaling problem will be there, and the final values will be always very higher. So it doesn't represent a good thing in a good manner. So what is again mentioned in the transformer paper is a frequency based approach. Okay, so you can see that it is a here the sine and cosine values are assigned for each position. Again, I'm not going in depth to this. I will just tell you what it is or what we have to do in the application point of view. So what we finally need is we need a matrix like this. So here I have taken an example where the maximum length of a sentence is 5, 1, 2, 3. Yeah. So we have maximum 5 positions in a sentence and our input feature dimension is 4. For an example, in normal cases, this length can be very high up to uh, 50 or 100, and this dimensions, as you know, it can be like large, like 512 also. So what happens is in normal applications, what we do is we initialize a matrix like this with all 0 values. Then we fill all these values. Okay, so this value, the first column, first row, first cell will be. So you can see in this, the even positions will be filled with sign value, odd position will be filled with cos value. So the first position value will be position is 0, I value 0. So we will fill both zeros here. So that value will go here. The next in this position 0, this is I1. Position 0, I2, position 0, I3. Similarly, position 1, I0. So in similar way, you can fill all these in this complete matrix using these two formulas. So if you're taking position 0, I will consider sign value. If it is position 1, I'll be taking cos value. I'll be filling these values here. So even and odd. So this has been very efficient and effective. Why we are taking both sine and cosine? Because we need maximum distinctive values for each position. So I know like it's to be explained in detail. You can always look over this. And there are different position encoding algorithms also. There is dynamic we are also doing. But in the transformer paper, they have mentioned the static one was showing better results, almost similar results. Okay. So what you should understand is when I encode a word with in position 0, this value, this first column value will be added to that word. If I'm encoding a word in the third position, 0, 1, 2, this column value will be added to that. So each position is now encoded to a single value. That is what you have to understand from this. So these are the two basic pre-processing uh, uh, steps you have to do before you load your data or like before you load your input into this transformer. Anyway, since this annotation is not working, I will switch to my laptop. I will just a minute. I will just switch the screen share. Okay. Okay. I have this. So, like we mentioned, I will just show the torch.nn function here. So these are the two, what we explained are the position encoding and input embeddings. These are the two pre-processing steps which we have to do before we before we load the input into our transformer. So to load, so this is the way how you can do this transformer in a PyTorch algorithm. So I think you had a class on PyTorch, right? Can anyone just mention that? You had an introduction to PyTorch, right? Can anyone reply in the chat? Oh, I believe that. Yeah, cool. Okay. So you might be knowing what is import torch and import torch.nnsn. So just let it be imported. So nn.transform function, these are the main parameters in the transformer. So what you should know is, like, you should specify the D model. D model is again the dimension, what we feature dimension. N head is number of heads for the multi-head attention. Similarly, can anyone just, is there any relationship between this D model and N head? Or should we give any, should there be any relationship between these two? If yes, then can anyone mention in chat what is the relationship? What I meant is, can we give it, say like my D dimension is, yes sir, it needs to be divisible, correct? Why? Because in what do we mean by multi-head attention? What happens in multi-head attention is we divide the complete dimension into by the total number of heads. Say like here I'm taking an example of 256 dimension and 4 heads. What it means is this 256 will be divided by 4. That means 64 dimension will be fed into like 64 into 4, and each 64 dimension will be fed into one head. And similarly, so we will have 4 heads, and 4 heads will be catering 464 dimensions, and later attention will be done separately, and later we will concatenate. So that is what, so we should be careful about these numbers, that total dimension and heads. Number of encoder layers is again the how many encoder layers you should have in the encoder. In the default, the original paper, it is 6 layers. If you see the bird has bird base have 12 layers and bird large has 24 layers. So increasing layers mean that much parameters are there. So again, you can mention these number of encoder layers, decoder layers, and dimensions for feed forward. If you have seen the encoder architecture, there's a feed forward network in the end of that, which gives the number of dimensions after feed forward. In the original paper, again, it was 2048. So here I have taken an example of this 256 dimensions, 4 heads, 3 layers each for encoder and decoder, and 512 dimensions for feed forward. So like for an example, I will see like what happens if we take a non-divisible value. So it will throw an error, right? It will show the embedded dimension must be divisible by number of heads. So for 246 is divisible, 56 is divisible by 4. Yeah. So this is the just direct way of calling the transformer in PyTorch. You can directly call this nn transformer by mentioning these parameters. There are more parameters, like you can give the mask specific, you can specify a mask layer, and again you can have a custom encoder also. This is a direct way of calling. Just to see this, like can anyone put a guess on how much parameters will be here for this model? How much trainable parameters? This is a 256 dimension, 4 head, 3 layers each for encoder, decoder. Can anyone put a guess for how much parameters will be there for this model? Parameters, you know, right? What all weights we have to train. That are the parameters. Anyone wild guess on the chat, please? No one? So I can enlarge the screen. Okay.
Till there is a comment, yeah, just enlarge.
Yeah.
Thank you.
Just over how to navigate. Just a minute. So this is my code. Can you see the code now? This is the code for transformer. So what I meant is I have given a 256 dimension, 4 heads, 3 layers each for encoder and decoder, and feed forward dimensions 512. I believe that you are relating this to the transformer architecture, right? Okay. We can check the number of in the original paper. This is 512, and we have 8 heads and 6 layers each for encoder and decoder, and 2048 dimensions for feed forward. So, like we'll see how much parameters this model is having. So this, I think now the screen is visible. This is a code for checking the number of parameters in a model. This P requires grad because I have given only. I'm sorry, I think I lost in between. Am I audible now?
Yeah, Dil, you are audible. Yeah. Yeah, we can see your screen as well.
Can you see the screen?
Yeah, we can see your
Thanks.
screen.
Thank you. Okay, so this is the command which I used to see total number of parameters. P request grad specifies only the trainable parameters I need to know. So we'll just check the number of parameters. Okay. So I think you can see the value here, right? So it is 39, like it's 3,954,680. Nearly 4 million parameters are in this model. So now you know like why transformers are so computationally heavy model, right? So it is a really effective model, efficient model, but training is not easy. So this, and again, if you have to see what this model is, I'll just give a command. So if you just give the model command in PyTorch, you can see like what all are the layers, the encoder layers, the linear layer, features 256. So this is the input output of the linear layer. I will get the default dropout value is 0.1. This layer normalization and dropout are the regularization technique. So this is the first encoder layer. This is the second encoder layer. And sorry, 0, 1. So first, second, and third encoder layers. And similarly, I have the decoder layers. First decoder layer, second and third, and outputting. Okay. So I'm not going to the training of this model because it won't be. I won't be able to cover this in this one lecture. So this is the most basic direct way of calling transformer. You can use this when you have to directly use this NN transformer or like the complete transformer architecture. When you have to use this complete transformer architecture, you can directly call this, and you can again check the model. And what goes into this model? So now we have created the model. We haven't given any input or output. So the parameters to this model is we should give a source parameter. Source is a sequence to the encoder, the input. Like the previous example we saw in the slide, the sentence or the position input embedded, positionally encoded sentence will be the input to this model. And we should also give the target sequence. In the lecture you might have heard, you will have an input sequence and a target sequence. So again, the shape of the input sequence will be SNE, where S is the length of the input sequence, N is the number of batch. Like we always train, when you train models, you will be training it in batches. Say we have a corpus of 100 sentences, and we have made batches of 10 sentences each. So we'll have total 10 batches, each batch containing 10 sentences. So here the N will be 10, number of batches. E is again the D model, dimensions of the embedding or feature dimension. So like I'm just this, I'm not training the model, I'm inferring the model actually. I have created a model. I'm seeing like what output I will get if I give a source. So randomly I'm generating a model with input sequence with maximum 6 words of 12 such sentences with 256 dimension, and output sequence with target sequence with 10 words, and the other two are same. So if I run this model, what I will get is output is output of the model. The output will can anyone say what will be the output shape of this? Can anyone just comment what will be the output shape? The output of transformer will be always, yeah, correct, same as the target sequence, correct? So if you can check it, the output will be having the same target sequence. So this is a basic how to call a basic transformer method in PyTorch. I have not included the training side. I will just one problem with PyTorch is PyTorch doesn't have an inbuilt training loop. You will have to mention the training loop in PyTorch. Keras has a training method. You can just call the model.train. So I will just show you a basic training loop in Python. Before that, I will just show you. This is a code snippet of how to use an encoder layer. So those are not familiar with PyTorch, you should see like we'll always this class method is used in PyTorch. So if you are using directly, instead of calling direct NN.transformer method, you are creating a transformer model yourself using this transformer encoder and encoder layer function. Okay. So I'll just explain. This is not a finalized code or something. This is just a code snippet. I'll just explain how to navigate in this code so that later you can refer to this. There are good tutorials available, PyTorch tutorials itself available, and later also. So what you should see in a PyTorch code base is always look for this forward function. So when you call a model, so when I call a model here, when I call this model, what happens is that forward function gets instantiated. This might be covered in the PyTorch basis, but still I'll just cover this. So what happens is when I call forward, first this step will happen, self.encoder of source into square root of the model. So what is this? This you will have to, this self.dot function you will have to check in your init function. So this will be initialized here in the init. So if you see self.encoder, you can see that is the embedding, which we have discussed in the previous slide. So what we are doing is we are embedding the complete source. We are making an embedding layer, and we are putting our source into that embedding layer. What it means is the source sentence is now embedded. Then we are scaling it using the square root of the model. Then again, we are feeding the same source into positional encoder, pose encoder. So you can check it here, self.pose encoder. What is happening here? There is a positional encoding function. That is a different function. I have not included the code of that here. So positional encoding is done to that input. So again, positional encoding is done. Then we are doing this source is again put into here with the mask. We are doing a transformer encoder. Again, see that here. You can see the it is a transformer encoder function called. Then output is a decoder. Here decoder is as a linear layer. So I've just included this to show you how to navigate in a code base in PyTorch. And like you can do it yourself. Just understand that everything happening in this forward is what we discussed in the architecture, or like what you might have seen in the architecture. Only thing is you have to go through this forward function one by one and see what each function is doing. Everything might not be self also. Something might be already defined functions outside. So you can see that. So this is a way they have a transformer model is built using transformer encoder layer, not directly by using NN.transformer. You can see here decoder is just a linear layer. They are not using any attention in decoder. So such models are also there where you use complete encoder for encoding and using a just linear layer. You the decoder function will be just a linear layer. Okay, I will explain just the training loop also. How a training loop, basic training loop looks in PyTorch. Again, this is not a complete training loop. There will be much more parameters, but this is the basic one. You can train a model with this loop also. So always you should mention the criterion. What do you mean the criterion? Like how do we backpropagate? We should have a loss, and we always try to minimize this loss. So criterion is what metrics you are considering for calculating the loss. Here, say I'm using a cross entropy loss, most common for classification problems. Okay. So my criterion here, I should define my criterion first. Here the criterion is NN cross entropy. This is an arbitrary name. Okay, you can put it anything, but generally we put it criterion. Then we should mention the optimizer, how we should reduce this, how we should update our weights. That is optimizer. The normal one which you have learned in neural network might be SGD, stochastic gradient descent, right? Here I'm using an Adam optimizer. Okay, there are different optimizers. Always look for the original documentations of this. So if you are using this one, look for torch.optim.adam documentation in PyTorch. So you will get to know what are the advantages of using an Adam optimizer over SGD, where you should use an Adam or where you should use an SGD. Okay, so these are the two things which you have you should specify before you start the training loop. You should have your loss criterion and you should have your optimizer. Then you should, now you are going to train. So I have taken a very small epoch of 50. Epoch is total iterations. So I will be iterating 50 times to train my model. 50 is very low number considering any deep learning model, because you have seen the previous model, there is 4 million parameters. So it will take a large number of training steps, and the data required to train that much parameters are also very huge. Okay. So again, there is a train loader functionality in PyTorch that you can see in the dataset loader. I'm not explaining that. So here what I'm doing is for each batch inside one iteration, I will go through all batches. So these inputs, say these are my, say I have a batch of 10 sentences. So first batch will have 10 input sentences that will be fed as a source. Then this is the output, target labels for this input. So here we just call the model. So these are the predicted labels, output of the model. Now, based on the criterion, so criterion will be, this is my predicted value, preds is my predicted value, labels are the original target values. Between these, I will find the loss just by calling this criterion function, because it is already mentioned here. So now the loss is calculated, then just you have to call optimizer.zeroGrad. This is ensuring that the optimizer gradient is put to 0 before every step. Loss.backward, you do the back propagation. Optimizer.step, you do the updation of weights. So this is the basic back propagation based weight updation in any deep learning architecture. So you should have these minimum steps in your training loop. So what happens here is the model predicts an output, loss is calculated based on the loss. This optimizer.zeroGrad is to ensure that your gradient is 0 before backward step. Okay. Otherwise, it will be the gradient will be kept on adding. So to remove that, we have to mention this command. So loss is calculated, then the loss is propagated backwards. Based on that, you update, based on the optimizer, you update your weights. This is done for the first batch, again for second batch, third batch, and for complete 10 batches, you do this. Then you go for the next iteration. So after each iteration, your loss is supposed to come down as the model is learning. So this is a basic training loop in PyTorch. There will be a lot more parameters and all based on how complex your model is. Yeah, so I just wanted to explain this model. So here I am not explaining the training of transformer model. It will take a lot of time and it will go in real depth. Okay, because you should, at the main, with any NLP application, what you should see is your data should be ready for the model. So there are a lot of transformer based models and there are a lot of very deep architectures. And also one suggestion I would like to give is always focus on the pre-processing of data, because that is very important. You can build a really complex, efficient model, but if your data is not streamlined for your model, your results won't be good. So there is a lot of things to be done in pre-processing, especially in NLP applications. You should see whether the pre-processing is apt for the model. So this is a way like you can implement transformer and you can train the model. I know this was just a basic overview. I would like to introduce you all to an open source library and an API where you can have all these pre-trained models and where these training and all can be made a little more easier. So have anyone worked in Hugging Face transformer library? If yes, can you put yes? Anyone heard of this Hugging Face? Right. I guess nobody has used it. So I'll just introduce to this Hugging Face. This is an open source AI community actually. Okay, Nasya has worked on. Okay, so those who have worked might know it, but just this will be just a very brief explanation of or an introduction to Hugging Face. Okay, so what is the best part in Hugging Face is it has a lot of pre-trained models. Like there are 95 transformer-based models, all pre-trained models available in Hugging Face, and it if you see that philosophy is to reduce this compute, because everybody won't be able to train a 4 million parameter model. 4 million is a very basic model which I have built. So if you are building a real world model, so if for especially for a very deep architecture, then it will be in 10 million, in that range, your parameters range. So it won't be easy to train a model in that. So the computational resources required to train such a model is very huge. So what we do is mainly we rely on transfer learning. Transfer learning is we depend on a pre-trained model and we try to fine tune this. So Hugging Face has made this a little more easier. I'll just introduce, go through how to install a Hugging Face transformer and how to use the basic features in this. Okay, so you can install directly from pip or from Conda or from or you can from their GitHub page also. So I would like to show this each code by code, so it might take a little time. By pip, you can directly install Hugging Face. If you are using in your local system, I would suggest to create an environment for this one and separate environment and try installing this. Okay, so transformers is their library name. Hugging Face transformers there. And they have very extensive documentation. This transformers is their library name, and they have around 95. So these are different transformer based state-of-art models. They have all these models pre-trained available. So like, yeah. So now we have downloaded the transformer library. And the most direct, easiest way to infer a model, what I mean is where you have to use a model directly, is to use a pipeline function, where you are not fine tuning or developing a model, but you have to just use. So you have a project where you have to do sentiment analysis. Then you have a pre-trained model already available in transformer library in Hugging Face. There are a lot of sentiment analysis models. You can select any from there, or you can use a default model. Similarly, these many tasks can be achieved in the Hugging Face pipeline models. You can use it for sentiment analysis, text generation, name entity recognition, question answering. So all these applications can be done. So we'll just go through how it is being done. So you have to call the pipeline library from transformers, import pipeline. So pipeline, when we call this, it imports, it caches all the pre-trained models and their tokenizers. Okay, so now I have to do a sentiment analysis. So I will define a classifier. So how to define it? It's just you have to mention pipeline of what task you have to sentiment analysis. So I have to do a sentiment analysis. So I'm just calling it pipeline of what happens when I call this function as it is downloading it retrained model. So which model is being downloaded here? It is Distilbert base uncased fine-tuned SST2 English model. So it is a Distilbert model fine-tuned on this dataset. Okay, this model is called. So here I have called a already available transformer model for sentiment analysis. We can see what is it doing. So what is sentiment analysis? I will give a sentence or a word or a paragraph. It will give whether it's a positive sentiment or negative sentiment. So this session is boring. I have given. We'll see what is the sentiment. Okay. So this model is predicting this is a negative sentiment and it is with a score of 0.99. So this is how accurate the prediction can be. Okay, so we can try another. So I love to travel. So it is a sentence with positive sentiment. So this is very basic application and it's a pipeline model which I've used. That means I'm directly using this model. I'm not changing anything. I'm just inferring this model. I'm not doing anything of my own to this model. I'm just using this model. Say your application is to just use a transformer model. Always you can go for this pipeline. It saves a lot of resources for you, right? You don't have to compute it. But problem is you can't say like this is being trained in this SS2 English dataset. So if your data set is completely different, then your results may not be good. Also, you can mention like you can mention a specific model for this. So like here, this is a specific model for sentiment analysis available in Hugging Face. So what I have to do is let me call another classifier to pipeline. My function is to do sentiment analysis. So I should mention the model name here. Okay, here the model is equal to. So I mentioned here I need this specific model for sentiment analysis. So you can see in the documentation what all models are available for each task. Okay, like you don't have to like I didn't write it on my own. I have searched in the Hugging Face documentation. I got to know that this model is available for the sentiment analysis. Let me see. Okay, now this model is applied to the classified 2. This uncased case means most training in most models they do put all the values into smaller case before training. So I will see how I'll use the same sentence and see what is different in this. So here you can see the label is in 5 stars. So what is different from the previous model is here it just classified to negative or positive. This NLP town bird based multilingual model classified in the star basis. Like 1 star is negative sentiment, 5 star is maximum positive sentiments, and it gives a score. So these are different models available. You can check on this pipeline and see like what are the different models available in this. Again, like we'll also do one more task. This was sentiment analysis. Like another task which is available is text generation. Text generation is like you give a sentence, the model will fill the rest sentence. So it is using GPT-2. GPT-2 is very powerful transformer-based deep learning model, general purpose transformer. GPT-3 was kind of very hype last year. So you are getting a pre-trained model. Like to train a GPT-2, I think it will require days in a multi-GPU system. So what you can always do is you can use these pre-trained models, you can fine-tune it over your data. So yeah, good question. Yeah, we'll go through that. This world is, I've just given a number. This is text generation, not a sentiment analysis. The world is I've given. So it is generating the text. Okay, the world is made as it should be at discover. So this is the what text generation is. Like so this will be based on how GPT-2 is trained. I think GPT-2 is trained on complete Wikipedia data. So this output will be dependent on that. If you want any specific output, then you should train it accordingly. So some Anand Kumar has asked to check this. The film is neither board. Yeah, obviously it will. It might show any sentiment, but the score might be less. If let me check the classifier. Classifier. So here we have to give a confusing sentence to the classifier, right? The film is neither interesting nor boring. We'll see what it will classify. Oh, it is classified as negative. So like but it is negative itself, right? Neither interesting nor boring. Okay, it is a mixed one, but it is classified as negative at times. But it has classified it with a good score. If it is at times for confusing sentences, it can come with a lesser score, means that it's not that negative. Let's again, this is another confusing sentence. We'll see how it is being classified. So it is also classified. So I guess this model classifies, if negativity is there, it classifies completely as negative. So again, like if you want to have a accurate, so like say like we are completely doing this for a movie classifications. So what we have to do is we have to import this pre-trained model. What we have to do is we have to completely take reviews, say like IMDb reviews, Rotten Tomato reviews, and again fine-tune this model with those data sets. Like you can expect everything to be ready with these models. So now we have seen a problem with this model. Like this cannot be completely negative. Okay, so what we have to do is we have to fine-tune this model. So how to do that? We'll just give a brief explanation again. So now we have done is just infer the model. We haven't done anything on the model. We just use the model which was available for us. So if we are going to do anything on the model, first we should pre-process our data. So again, as we mentioned, like there is input embeddings, the vocabulary is built and all. We have seen that in the initial first slide, right? So every model has its own tokenizer. Tokenizer is how the word is converted into number or index, and then how it is embedded. So if you are going to use a pre-trained model and fine-tune it, you should. So fine-tune means you will have your own data set, right? Say like for the same example which we were talking about, we want to build a sentiment classifier for movie reviews. So based on the movie reviews, you should put stars to the reviews, okay, to the movie. So but the model the pre-trained model which is available is not doing it accurately. So I have a data set from IMDb or from say like Times Now's movie column. I have a lot of reviews and I have star ratings. So now I should fine-tune the already bird-based model using this data set. So this input data set, I have to convert into tokens, right? Or into numbers and then to embeddings. So when we do that, we should use the same tokenizer which was used in the original pre-trained model. For that, again, this transformer library is giving an auto tokenizer function. So you can see from transformers, you should import this auto tokenizer. From auto tokenizer, so say that I am going to fine tune this bird case model. So then I should use the same tokenizer to pre-process my dataset, whatever dataset I am having. So like say this first, I should again this will download this tokenizer. This is the tokenizer which was used while training BERT based case, because I'm gonna fine tune this model with my data set. To process my data set, I should use the same tokenizer. Process in the sense I'm changing each word into a token. I think you understanding this, right? So like, okay, I've already typed an input here, encoded input. So like, this is my input sentence. So like I have attention is all you and two exclamation marks and all. You see how this is being encoded using this tokenizer. This tokenizer is of BERT based, so I'm calling this tokenizer here. I'm sorry, I think the code is visible, right? I'm sorry, I didn't zoom it later.
It's visible now.
Okay, fine. So see, like now I have given to this tokenizer. This is my input after tokenizing. These tokens are based on the BERT-based case, this model. Okay, you can see 1, 2, 3, 4, 5, 6, 7. So you can see there are little more numbers in this, right? So it is more than the input. You'll get to that. This 101 and 102. You'll see what these are. So these are tokens for each word. Okay, attention is 1335, and in some models they even split one word into two, but they will add a prefix for that also. Okay, so this is what the tokens of these words in BERT case, and so this 106 is for the exclamation mark. You can see two exclamation marks. You need is 1444. You see, so you can see additional. There's also token IDs and attention mask. So what this means is attention mask is whether if you are, so this comes in picture when you are padding or truncating. So in normal cases, all your sentences won't be of same length. So what we generally do is we put a padding. Padding means we'll give a maximum length of say 20 here. So any sentence less than 20, say if it is 15, 5 zeros will be added to incorporate it in 20 length. And that case, the last 5 numbers in attention marks will be 0. Means that you don't have to attend those things because that are just padding. Similarly, token IDs is again when you have the truncation, like which all tokens you should consider and which all not. Okay, so that is not needed now. So we can see like what these additional two tokens are here, 101 and 102. To see that, we can decode it using this tokenizer.decode function. You see that? Okay, so there's a CLS and separated token added. So this is a special way of tokenizing in BERT case. That's why I said like we should use the same tokenizer what the model has used. Because some models use say HTML kind of thing. Some models just put an under it might be end of EOS token might be used, end of sentence, SOS start of sentence tokens. So it will be different for different models. So always you should use the tokenizer which is of the model which you are going to fine tune. Okay, so this can be automatically loaded using this function. And again, now you have to call the model, right? Like for the class pipeline is for just inferring the model, like when you have to directly use the model. If you have to call the model, again, you will have to import auto model sequence classification. Detailed documentation of all this is available in Hugging Face. I'm just introducing you to this because this is very extensive domain actually, because there are a lot of models, lot of steps to be done to fine tune your model. So you can always refer to them. There are a lot of tutorials also available. I just in this 1 hour session, I won't be able to even go through top of all these things. Okay. So this is a way like, again, I have to use this NLP BERT based multilingual uncase sentiment model. So what happens is first you have to import this auto model sequence classification. You have to mention your model name. Now you have to download the pre-trained model from this using this library, and you have to download the tokenizer for this same model. So what happens here is this model will be downloaded to the model. See this one, you can see the model. See, that is that BERT model. It's a very huge model. So this is the BERT layer model. See, this is the model which we have downloaded now with all the weights as the pre-trained one. Now we have downloaded the tokenizer also. Now to fine tune it, you will have to load your data set, and either you can call a training loop like we discussed earlier, or in case of Hugging Face, they also have a trainer API which provides you where you have to just input your arguments and it will do the training. So you have to just call model.train. I'm not going in depth to these things. I just wanted to give an introduction to these things. It's already getting the time is getting over. So like those who want to research, like those who, if you have a really different architecture to build over transformers, obviously you can try from the scratch or training using your attention model and all. But I will say that training is very computational for transform models. If you want to develop over any already available state-of-art transformer models, obviously you can use Hugging Face. You can contribute to this community also, where you can pre-train, you can fine-tune a model and upload in the community. So explore this one. I feel this is a good resource. Like the website itself is a good resource. You can have all the documentations available here. You can see that all the models available here based on the tasks. Okay. Quickly, I will just go over my one project which I did. I'll just give a brief understanding of that. I won't go in depth. I know it's almost time. So lunchtime. I don't want to take away that. Sir, if I need to remove the position-wise feed-forward layer and some simple non-layer activation, just let me answer this question, then I will go to that. So if I need to remove the position-wise feed-forward layer and some simple non-layer activation and use all the pre-trained weights in attention layer. Suboyoti, can you just unmute and ask me? Like I didn't understand the question. Right? Arun sir, do we have the option for the participants to unmute?
Can you? Okay. What is the query?
Does the participants can unmute? Do they have the option?
Yeah, we can give them right. Yes.
Suboyoti, can you? Okay, Subyodi, just prepare the question. We'll come back to you. I'll just explain the project. I'll just give a brief understanding because it will take time to explain in detail. So my major focus was it was a computer vision application. I wanted to detect ships. It was a very niche application. Like I wanted to just detect ships over an image from satellite image. It was not a generic model. So to train a complete transform model required a lot of computation. So what I tried to use is a forced attention based approach. I will just explain what it is. So what I did is I divided my input image into different patches. So like not directly dividing. So the input image was of 768 by 768. I have divided into patches of 256 by 256 with a stride of 64. So like this single ship is included in many patches. Okay, so that's what I did. Then I classified these patches using a classification network, which classified patches which has a ship. Okay, so if you can see this first 5 images, all are of same ship itself or a carrier. But if the classification network work like this, and to detect which is the perfect image patch for a ship, I am using attention. So what I did is, why I named it forced attention means I am telling where to attend. So I have already created and curated query images where proper ship images are there. Okay, this is a pre-trained model. Like I pre-trained it with this query images and outputs. So what happens is this query images do a similarity match with this proposal patches, and it gives attention score for each patch. So the maximum attention score implies a proper ship. It is like the logic is little deep, and I do a non-maximum suppression to avoid other so if this box is selected, I don't want this other 4 boxes because it's the same ship. This I'm doing using non-maximum suppression. It's a very normal technique using object detection. And finally, I output these patches. I'll just show the architecture of how my attention model works. So why I had to do this is like this reduce the computational cost a lot, because since I am giving the query images, the parameters was very less. I have to just do a linear transformation and do the attention mechanism. So I have these query images, I have proposal patches. I'm using a CNN backbone to extract features from this. Yeah, studio this. Just a minute, I will complete this and get back. Okay. So I extracted features from these query images and proposal patches. Then I have done a scale dot product. If you have seen the attention mechanism, you might know why a scale dot product. Then this will give me the attention values, right? So the first column is, say these are the patches. First patch, how similar with the first query image, second query image. Say there are 30 query images till 30 query images. Then I do a summation column wise to get the attention weights for each patch. This is what happens inside that forced attention box. I'm not going it in detail. If anybody is interested to know it, you can ping me personally later because it will take a lot of time. Again, getting back to you to Sahar, like, can you unmute and ask me what is it about? So okay.
I was asking that if we remove the position-wise feed-forward network and just add some nonlinear activation functions, and
Okay.
we want to use the pretend weight in the attention layers. Means we don't want to train the attention layers. Yes.
Use all the pre-trained weights in the attention layers. Okay. So you want to change the positional encoding, but you have to like if you're using any Hugging Face thing, like you don't have to do the positional encoding here. It is being done in the model. You can directly input your like you only have to use a tokenizer.
So I was asking, I want to remove the position-wise feed-forward layers. Position-wise feed-forward layers. Just remove them and add some another.
Okay.
Just for ablation studies, I was eager to do. So how can I do those things?
Like you have to remove it from, like, in which architecture you are asking? In the normal transformer?
Yes, sir. BART.
In the bird.
Yes, sir.
So okay, you have to change the configuration of the model itself, right?
Yes, sir.
In Hugging Face, you have an option to do that. There's an option to download the model, and there's a .config method in Hugging Face where you can change the configuration. So, but you'll have to go through the model completely and have a detailed view of that overview.
Oh, yes, sir.
Like you can freeze the if I'm understanding it correct, I think you want the attention weights to remain the same like the pre-train, but you have to only change the feed-forward layer, correct?
No, sir. I want to remove the feed-forward layer completely from the network.
Yeah, you can do that. You can go to the config and you can extract. So, you want a part of a system and use it, right?
Yes, sir.
In Hugging Face, there's an option in .config option is there. I think you can extract the layers which you need from the and you can freeze the training weights there. But I haven't done it, so I'm not sure like how to do it. But there's a .config function. You can just explore in that way. Yeah. Otherwise, you can download a pre-trained BERT model, which is available otherwise, like in the PyTorch, and then you can remove the final layers from them. So yes, it should be available in Hugging Face also. You just check the .config functionality there in Hugging Face.
Yes, sir.
Okay.
Yes, sir.
Yeah.
So another question, in long format, the sequence length is maximized to 4,000, something long format. So okay. Can we continuously increase the sequence length? Or
so
it is
that is again,
yes,
like in that pre-trained model, you cannot change that because the tokenizer will be the padding of the tokenizer will be built according to that.
Yes, sir.
While fine tuning again, you can give a padding, but yeah, but it will be done based on the already downloaded tokenizer. So yes, better to that's why like always don't go for the most complex model or most simple model. Always see which model suits your data set. So and yeah, like developing a model is a very complex model is like that requires a lot of effort. But in real, when you come into real world problems, the most effort where you will have to put in any deep learning or NLP application is in pre-processing your data. So like those who are working in industry, they will know like they get very little to work on the model because model will be pre-trained. But how to customize your data for the model, that is where you have to put your effort and to find the right model for your data. And then later tweak on the model to incorporate how little changes or to regularize those things. Yeah.
Yes, sir.
I don't know how much you all might have got from this session. It was a lot and it's a really deep topic. Those who are interested in NLP, I will suggest like always go through the official documentations and the research papers. First time you may not get the research paper. You understand even the terms in the research paper, but as you read it again and again, things will get clear. There are a lot of concepts and it's very dynamic one. It's being developed like when we talk now and the next week, there will be a much more efficient new model coming up. There are a lot to learn in this session. So try to pick each topic, like starting from word embedding, positional encoding, attention. What do you mean by masking? There are different masking. Source masking is there, look ahead mask is there. So why we are doing these things? because these subtle things and small things will change the efficiency of the model a lot. So you all have to so if you are looking to real world applications, and you will have to get deep down in these models, then only you will understand what is happening. Never use this direct pipeline model for any of your projects, because this won't give you anything. Like, you're not learning anything here. Always try to download a pre-trained model and fine tune those models and see. Yeah, I think that will be the end of my session. If you have any doubts, we can quickly go. I think that's almost the time, right?